All right, Sean, I'm recording as of now.
Okay, perfect. Thanks. Okay, so some of you may know Josh has also been keeping track of feedback and stuff, trying to kind of have his pulse on the finger of the situation as well. And one thing that he thinks we ought to do, and I think this came as a suggestion from someone, is just kind of to have the instructor kind of kick off the sessions, the lecture sessions, to give an overview of what will be happening for this session, what will be happening for the day, and to kind of give a little bit of context and motivation for what we'll be doing during the session and kind of why we're doing it. So we're going to go ahead and try that today. And then I'll also stick around in the background and answer questions in Slack threads and things like that during the actual GP. But yeah, so we're going to get started with theory of computation and hash tables. I know it's a little bit of a mouthful. But the idea of this week is to give a little bit of that theoretical background, because that really informs things like, you know, like why we talk about scaling software the way we do. We talk about things like some of the logic behind how all this computer science reasoning even works. I mean, we don't go into too much detail. It really is just a very kind of surface level scraping of the topic. But again, the idea is just to be like, you know, and again, this isn't going to work for everybody, but I do know some people do find this sort of thing interesting. I know Stephen apparently found that Art of the Problem video interesting. I really like it as well. Yeah, they're pretty good. So yeah, you know, it's not for everybody. And again, not everybody, not everything, not every topic in computer science is for everybody. But, you know, again, the idea is this kind of having this wide berth of different topics to kind of delve a little bit into. And again, that the benefit of that is twofold. Is again exposing you guys to lots of different problems from different domains, so that you know, it's a lot harder to blindside you when some new problem comes around. And then, of course, other thing being is to, you know, people are, of course, interested in different things. So if we have kind of that wide berth of topics, people can kind of pick and choose what they find interesting, what they might decide later on to delve a little bit deeper into. Right. So, you know, I personally am not also even interested in every single topic we teach. Obviously, I have to be well versed enough to teach it, but that doesn't necessarily mean I have any sort of, I don't necessarily find it all interesting, for example. Even with just like theory of computation, like what's interesting about this particular topic is that every instructor has different things that they like talking about. Beej is the one who really likes the history stuff. If you were to ask Brady, he likes, because he has a little bit more of a background in like electrical engineering, for example. So he likes talking about going from those very, very kind of fundamental logic gates, like what you'd work with in like an electrical engineering setting, and like how to kind of build that up to even get to software in the first place. Like obviously there's a huge chunk of stuff just in there that we don't even get to talk about because we start talking at the software level. But he would like talking about a lot of that even lower level stuff. And of course, you know, as for me, I came from a math background, so I really like the computability theory stuff, which is why I linked that video. So, you know, people have different interests, and we all walk away with different takeaways from all these different topics. That being said, it is kind of difficult, and I was saying this in the post I made a little bit earlier, it is a little bit difficult to come up with a programming exercise or any kind of practical practice given this sort of topic. And so what we kind of opted to do for the actual topic, for the actual programming exercise as for this week, is to delve a little bit more into data structures in C, right? And the good thing about C and implementing data structures in C is that it's, of course, again, way less abstracted than what we've seen so far. Then the other time we've implemented data structures using Python. So this gets even more kind of raw and lower level, and we'll kind of see how, I guess I mean to say that, so the first thing we'll be doing is we'll be implementing kind of the array data structure that everyone knows and loves from JS and Python, lists in Python. And that includes a couple of things, like obviously we need to be able to remove from both ends of the array. It also needs to be able to dynamically resize. That's one of the big things that the array and list data structures, abstract away from you in both JS and Python. There's never, you never see that they have to reallocate, that they need to get more memory as a result because they got filled up to capacity. But this is something that we will see. If we want to implement something similar in C, this is something we're going to have to bake into our data structure. So we're going to kind of peel back those layers a little bit and again, glean a little bit more insight into what those data structures that we are very used to, that we know and love, what they kind of have to do under the hood and how in order to achieve that behavior. So the first 2 days will be with arrays. And then the second day, we'll start implementing hash tables, which again, another very much loved data structure that you guys use very often, i.e. dictionaries or objects in JS and Python. I don't actually know what they're called in Swift. I don't know what Swift calls them, so I'm just I should just use the language agnostic term hash table. But yeah, that'll be for the latter half of the week. So for today and tomorrow, as far as programming practice, we'll be implementing the array data structure. Okay, so quick little bit of context as to what we'll be doing these first 2 days. Does anybody, oh, sorry, I wasn't looking. Okay, Swift calls them dictionaries, okay. Anyone have any questions on just anything I talked about? If not, I'll let John get into it. Okay, and again, I'll stick around and answer questions in Slack threads and things like that. So yeah, take it away, John.
All right. So for today, we're going to be going back over a bit of memory allocation, memory reallocation, and strings in C. We're going to go over that fairly fast. I'm going to try to keep this to about an hour 15. One of the changes, we had talked about it originally, but we're going to try to keep these well up under the 2 hours allocated. So I'm going to go through those reviews fairly fast and actually just walk through the code instead of typing it all out. We intended to use Python Tutor, but we ran into a problem with each one. One of them just has a million steps because it's an iteration. Another one, Python Tutor doesn't support it. The type, and another one has another issue. So everything's going to be in. And then as far as the implementations go, they're also going to be in the editor and compiling them manually because Python Tutor is timing out on them because of the size of the operation. So I'm going to go ahead and share my screen here. And we already are recording. I guess, first of all, did anybody have any general questions? I'm kind of going to guess no because y'all didn't have anything for Sean, but I just wanted to throw that out there. Okay, I'm going to drop all of these codes. For the first three, like I said, we're not going to type through them line for line or we're going to be here for more time than we've got. But the first thing we were going to do was review of malloc. All three of these concepts will be important today in your independent project. So for the malloc on lines 2 and 3, we just have the preprocessor information before it's compiled. Of course, when you use Python Tutor, you don't have to use these, but these are just the libraries, the standard libraries, and the input-output library that we want the compiler to include before it runs the code. Then we have our int main void. We've got three different things here. On line 7, we are simply allocating 100 bytes. I think everyone's pretty clear on that. This is us dynamically allocating arrays onto the heap, and hopefully everyone's aware these can be resized with realloc. Can anyone tell me, type in why we can resize on the heap, but we can't with realloc, but we cannot resize on the stack when we just allocate arrays on the stack like we do down here? These we're either declaring straight up a number, or we're dynamically allocating memory manually using size of character, size of int for these A, B, and C. And these were just with this notation, we're allocating arrays on the stack. Anybody have any idea why we can add onto the heap, but we can't reallocate onto the stack? The short answer is as Stephen is saying, the stack is bounded in size. So you have to be able to malloc, you have to be able to realloc, or to be able to realloc, you have to be able to malloc. But so when you use this terminology or this syntax, you actually cannot use the realloc. And the reason it prevents you from doing it is, like Stephen said, the stack is bounded in size. And the heap doesn't have infinite size, but it's got potentially a lot more size, because it's the heap, if you kind of think of it as working from the bottom up, and the stack has only got as much room above it as that is physically available. So C just prevents you from being able to do this with the syntax and the way that it's set up. So in this case, like I said, we're allocating 100 bytes. In this case, we are saying 200 times the size of the character, which of course is always 1. So we're allocating 200 bytes. And in this case, we want to be able to have 300 integers times size of int. And we know that size of int is always greater than 1. In this case, we're just saying 100, 200, and 300. Anyone have any questions? We'll let people type real quick. That's a good point Sean makes. Why even include size of character than if we know that it's 1 and it's good readability? Which I didn't think of that point, but that's definitely a good point that Sean's making. Couple people still typing. And what this print statement, I'm going to go ahead and keep moving while people type, and we'll move back to that, or Sean or other staff that are in the channel will answer these questions as I'm talking. This print statement is showing that pointer and array equivalence. Here we've got a pointer. Here we're just simply using the array. But this notation, and the same here, this notation, whether we're just using the array notation or we're using the pointer notation with the pointer arithmetic, it's equivalent. Why is it equivalent? Why is it the same using array notation as it is with pointer arithmetic? Real simple, short answer. Yeah, array notation is syntactical sugar, and it's doing the exact same thing, Kai, exactly. So when we run this here in a minute, we will see that both of these return true. They'll return a 1 for true because you just have a conditional, or excuse me, an evaluation here. So it's returning a Boolean. Yeah, see, Sean answered the questions about the memory allocation being the same. James had another question. And then here on 19, 20, and 21, because we dynamically we're handling this memory, we're just freeing it. This right here is because we didn't use these in the demo, and it'll throw a warning in the compiler because we use that wall and Wextra. By habit here, you certainly don't have to use them, but this prevents that error from being thrown, or that warning actually from being thrown. So we're just putting void for these and returning 0 to exit out. So if I were to compile this, and just sort of a little side note, you can just actually say GCC and this right here. It will not add all of these errors, and it will not actually rename, because here we get the file name malloc. I think it does something like a.out would be your file if you didn't use it, but you don't have to have all this with it, but this is just the way that we do it. And as you see, we return true and true, showing that this is functioning and that this notation, the array notation, is the same as pointer arithmetic, because as Kai said, the array notation is simply syntactical sugar. And by practice here, we free ABC. We're accounting for D and E not being used by the program. Recall that we used F here. So something like I was showing, it's a little bit off topic. You can actually just say GCC malloc dot C. And if I look at my desktop, right here, you have a.out, and it's the same thing. Just something to throw in, and you get the same. Stephen, the void D is just, it's because we're calling, you can look it up in the documentation, but this wall and Wextra is just enabling all these warnings that we throw. To keep it from throwing a warning on these two, this syntax is basically acknowledging, hey, we didn't use D and E that we declared here in this program. We used F right here, but we didn't use D and E. You don't have to have this. But if you don't do this, what it will do. See, it's just, all it's doing is preventing these warnings. Make sense? Yeah, I don't know specifically why that syntax does it, but that syntax, that's James. Hopefully Sean can answer that, or somebody. I don't exactly know. It doesn't clear it from the stack. It's basically, I think it's just accounting for it in the program, but I'm unsure. Sean can maybe answer that. Tommy, that wall and Wextra just enables, if you go through and Google it, it'll show you all of the warnings it enables. You see these warnings that I've got highlighted right here? It's just this unused variable. If we just said GCC malloc.c, like we did earlier, we just get this because we're not naming the output file, the O flag with the new name malloc, so that I'm running it with malloc. It's just creating this instead of creating this compiled file right here. And you see that we didn't throw these warnings that we did here. Does that answer your question, Tommy? Cool. Cool. I'm going to keep moving on to the realloc. Feel free to keep asking questions in here. Sean has been active answering them, and they're all good questions. Yeah. That wall and Wextra used to have different names at some point back in time, but they changed it to that wall and Wextra, which a little bit more confusing. I forget what the original names were, but to me, they were more semantic, but that's just what we use. And like I said, you can look them up and see all the different things that it enables. Okay. So I'm going to drop this code into the channel. Would y'all like if I drop the code beforehand, since I'm not typing these out and they're all on the screen anyways for these few that we're running through? Okay, I'll do that. So let me drop malloc. And then I will do the realloc. And we will go through this real quick. So for this, we're just going to go back over realloc and any just general C questions that you may have. Remember, realloc can only be used when we've used malloc, when we're dynamically managing the memory by hand. Yeah, Sean just covered again what we were talking about, why that void was in there. I think Stephen had asked the question and I had answered it, but it's just preventing the warnings from being thrown. That's all it does. If the wall and Wextra was not in there, it wouldn't even matter. Tommy, no, I don't think so. But Sean can probably give more insight onto that, but those are on the instructional side of the GitHub. Is there something in particular you were looking for, Tommy, or wanting? Yeah, this is the quickest way with the way we're doing things currently. So here you just have your preprocessor information again, int main void. And we're just allocating, once again, like Sean said, we're just saying the size of int for the readability. Cool. On line 7. And then we're iterating through on lines 9 through 11 from 0 to less than 100, of course, because we are 0 indexed, and we are just setting, we're using array notation, the index equal to I. So index 0 will be 0, index 1 will be 1, and so forth. So we're dynamically managing the memory. We're using array notation here. Remember, those are interchangeable, but this allows us to be able to reallocate when we use this syntax. If we had used the other syntax, just using array notation, it goes on the stack. We cannot reallocate. So we're allocating memory to the heap one more time with the malloc. That I did not know. GCC is pronounced Gucci. Cool. Yeah, that goes way back, I think, to like the Bell and AT&T days of when C was, I always say GCC too. It's a good question because these, like I said, this terminology goes all the way back to there's only like 2 other options out there, I think, but the GCC compiler or the Gucci compiler, if that's what it is, goes back to what was first Bell Labs back in the early 70s. And then when it shifted to AT&T, maybe in the early 80s, when C was, I guess, private, if you could say, before it made its public appearance in 1978 or such. I like the Gucci compiler name better. James just asked a question. Hopefully Sean can answer that. I am not sure if that clears it from the stack or not. So hopefully Sean can answer that, or it looks like Ryan's typing real quick. Okay, so we've iterated through, and here is just a print statement to see what we've got at 50. We would expect to have 50 at 50. We'll see that here in a minute. Alias Gucci. Now we're reallocating here to grow the space to 200 ints. Remember, when we realloc, the previous values under the hood are copied to the new space, a nice little feature. And now we're starting, because we reallocated and we've copied the previous, we still have from 0 to 99. And now we're going to go from 100 to 199 and do the same thing. So 100 will be 100. 101, index 101 will be the integer value 101, and so forth. We're testing that here with simple print statements that we'll see in a minute. Then here on line 25, we're actually shrinking the space to 75 integers. Any space above 75 is deallocated. So here we're just showing a 50. Obviously that space is still allocated. Here's something sort of interesting that we may have a little bit of a discussion about. This is undefined behavior. Maybe it works, maybe it doesn't work. Index 150 has been deallocated, so it's invalid to use it. It might still work, it might not. Like I said, we can have a discussion about that. And then we free P in itself, the entire array. After we've freed all of the pointers to the integers within that array, we free the actual array itself, and we try to go back and access 50, which was within the limit of the 75 that we had reallocated to, and we'll see that behavior as well. So all of that said, and we get what we were expecting. We get 50 here. We reallocate and we get 50 and 150 because those are all available. And then for the undefined behavior, it still accesses them. Anybody want to maybe opine on why it may still be able to access them, even though there's theoretically it's invalid to use it? Sean, did you want to comment? I read up on this, but I think maybe you could more succinctly comment on why, based on what the allocation and deallocation is doing and why it potentially can still work. It is still there in memory, exactly, Addison. Like we talked about, I don't remember even what context it was in, but Beej was talking about, and this is that whole thing goes back to deleting things on a computer, but they're still sitting there. You have just removed the reference to them, and they haven't been reused yet. So if you were really dealing with something that was really secure, you can go back through and manually clear that out as well. But just because you've moved the pointer, like we'll see later on when we do the stack and the queue, and like we've seen before, just because you're moving pointers and reallocating and whatnot, it's still sitting there physically in the memory of the computer. Like I said, Sean may be able to add to this or to. Tommy asks, realloc to a smaller size will free everything above it. Yes. And Sean, that goes back to James's question, and Sean answered that with the previous one. I'm going to let y'all finish typing here. Sean added some to why this undefined behavior. He kind of gave a good definition of undefined behavior above, and he's also explicated on it a little bit more right here. I'm going to move on. I'm going to drop this code ahead of time as well. Copy. Here's the last piece of code that we'll be going over as a review. Okay, so we have our preprocessor information. This time we include string as well, since we're going to be utilizing string. Remember in C that a string is simply a pointer, an array of pointers to a character. Does the function malloc keep track of where the next available space in memory is, or is that an OS task? I believe the operating system handles that, but I'm not 100% sure on that answer. I see Sean just replied. Yeah, it's the operating system. Thank you, Sean. Okay, so here we're doing two different things. We're doing an array of 10 ints. This is going on to the stack, remember. We're dynamically declaring an array of 10 integers with B using a pointer and the malloc in size of int. So this can be reallocated. It goes onto the heap, as we've been we've been talking. We do the same here with a character. Here we've got a new syntax. We're not going to dive into this too much. We talked about it a little bit in before hours. You'll deal with it again in your independent project and you can go read on it. Basically, in short, we've created a pointer to a pointer with this dynamic memory allocation. We're already using a pointer and we're creating a pointer to a pointer. Why? Does anyone want to answer why we're making a pointer to a pointer with this array of 10 characters, this string? Why are we having to make a pointer to a pointer? Kai is talking. Seems like wrapping everything in boxes in CSS. Remember that a string is just an array of pointers to a character. Now, because we're dynamically allocating the memory and using a pointer, we're pointing to the index of the array, which is pointing to a character for the string. So we're creating a pointer to a pointer. It makes a little bit more sense when you start dealing with it. Tom made a real good quote about that earlier in before hours. But anybody that wasn't in before hours, I would encourage you whenever they are offered to attend them. It was really good. I had actually commented to Ryan how good it was, and it's worth going to. I will sit in on every. Okay, yeah. I think it was announced in the channel by Brady on Friday, but I will make sure that we do a good job of announcing those. I'm unsure if it was recorded. Brady led it. Tom Tarpey was also in there, but I can check with Brady and see if it was recorded. I'm sending a message to him right now. Yeah, what Sean's saying, the easiest way to remember it is the way like a two-dimensional an array is another way of thinking of it. It's a pointer to a pointer. It's all it is at the very lowest level. Remember, Sean mentioned that these are not initially given the value of null, so we're just going to iterate through that and give them a value. None of those 10 pointers point to anything, so we're just initializing them here. Strings are essentially arrays of characters. If we want an array of strings, that's an array of arrays of characters. Yeah, well put. Why do you malloc 10 bytes to D? We're not mallocing 10 bytes. We're saying 10. Justin, on line 12, we're saying 10 because remember, we're wanting 10 characters like we did up here on the stack. 10 times size of character. Remember, the size of character is 1, but the reason we're doing it is for readability. I misspoke when I said that this was just for readability earlier on line 9. This is because the size of an int is greater than 1. And because of the way C works, for it to be able to iterate, it has to be able to know how big it is, and that's why we have to declare the type. Here it's just for readability. We could have malloced 10. Yeah, the pointer. How much are characters point character pointers, Sean? Are they 8, I believe? So I misspoke on line 12. I think they're 8, if I'm not mistaken, but somebody can look that up if they want. So here we're just, yeah, Justin saying he thinks they're 8 as well. The before hours was not recorded today, but in the future, we will make sure that they're recorded. And then right here on line 18, we've got an array of 10 pointers that are pointing to null. So we're just making a string here that says I'm saying in line 12 is specifying the number of arrays of characters we're planning on holding in D. We're just setting the pointer to some string here. We've named it to be lambda. Right here on line 20, we have to allocate space for that. Remember, these are all have just been initialized to null on line 15. So we're saying string length of some string right here. So we've got 1, 2, 3, 4, 5, 6 plus 1. Why do we do plus 1 on line 20? Got 6 characters here. Why do we do plus 1? Yep, the null terminator, Brad. And now that we've allocated the memory for it, we just use the string copy. And so now we're going to have lambda being pointed to, and then a print statement. And then we're going through here and we're freeing all the memory on line 26 through 28. And then, yeah, Sean's saying each individual string might have a different length. And that's why here we actually had to malloc for this string for this trivial lambda that we set up here. And then we're freeing each of these. If we had not initialized these to null and we use this free, this would theoretically crash here. And then we free D itself on line 30. And we're voiding A, B, and C because we didn't use them. Once again, this is just to prevent warnings from being thrown. Compile it. And our one print statement shows there that it contains lambda. So it allocated 7 spaces there. I think if you had just given it 5 spaces and you ran this over, I actually don't know why that's working. Yeah, I'm wondering why that's working. I would have actually this I forgot about the exclamation. This was 8 that it would have been allocating. I yeah, I thought it was going to cut it off as well, but maybe someone has an idea. I honestly don't. I'm not. Does anyone have any questions about this, about any of the syntax in here, what we're doing? Any questions over what we've reviewed? If not, I'm going to let everyone go to break for 5 minutes, but please throw out any questions that you may have. And this is going to end up running past what I had intended, but we'll implement the stack next. Yeah, it's still summing up my C experience the third time around with it. Sean, do you have any idea on line 20 here when I went through and I manually allocated?
Wait, so okay, what happened? So you malloc 5.
I just put 5 in. I saved it for sure and just take my word for it. And then I compiled it and then we ran it and it's still doing the entire, it's not just doing this and not in cutting off the new line and throwing it right in front here. It's printing out the entire lambda exclamation in a new line.
My guess would be the string copy. But let me check again.
This is just a detail that was not in the GP. I just was doing it just to show it, and it didn't act as I had expected. So I figured it was at least worth bringing it up since I. I think while Sean's looking at that, everybody can take a break. We'll meet back at 5 after the hour. So at your time, that will be 9:05. Is it necessary to free memory if we still have the line below that says free D? Nedim, are you meaning because on the line that you're pointing to, we're freeing all of those arrays, and then in the second line, the free D, we're since we've got a two-dimensional array as we were discussing, we're freeing that outer array. Yeah, like Sean is saying, and like I was touching on, we've got an array of arrays. So we've got to work from the inside out as far as freeing the memory. And then once again, the void is just avoiding the error or the warnings. All right, about 2 more minutes and we will get started again. All right, it is 5 past the hour. Hopefully everybody got a chance to stretch, grab another cup of coffee. I know I did. Guy, it's a good article. Somebody that I went through CS7 with, he was a Navy SEAL and he wrote an article about, actually I think it wasn't him, it was Richard that wrote this. He interviewed this guy extensively, and it's way off topic but worth taking a look at. All right, we're going to get started here. So one of the, yeah, his book is really good. I read his book, Tommy, after Richard mentioned it to me. And like I said, he went back and forth with him a lot and wrote this article, which is really it's kind of like the cliff notes of part of his book, but the article is definitely worth taking a look at. And if you liked it, taking a look at the book. But so one of the changes that we made is, like I said, we're trying to keep everything relative to the independent projects, to the sprint, to stuff we're going to use both in interviews coming up that we all may have or will have, stuff that could potentially appear in there, and to the real world. So we've gone back over a lot of the points that are confusing in C. Memory allocation, reallocation, strings. We've had some great questions. Sean and the staff have given some great answers in the channel. We're going to move on to implementing a stack in C. This is very relevant to me. If you can implement a stack, any data structure in C, you can implement it in any language that you're asked to do it, because this has us doing all the low-level handling of the data structure. So I will be typing this one out by hand. Please feel free to point out any errors that I'm making. And we're going to go through this, and then we're going to do a queue. We're probably going to run right up to the hour. That's my bad after I just promised these were going to be an hour. But at the same time, I just don't want to punt all the questions or gloss over things that deserve more attention to help everyone's understanding of what we're going over. So we're starting out with the type def of a struct we will name stack. We'll have an int, the top, that's just the top of the stack, the index. Unsigned int for capacity. Why can we use an unsigned int? And we'll use a pointer for all of the data. Why are we using an unsigned int? Just a little review for the capacity. Yeah, capacity won't be negative. So this is just a struct that represents a stack that holds an integer representing the index of the top of the stack, the total capacity that the stack can hold, and a pointer to an array of integers. If it's above 2.1 billion, Sean, I don't know that that's actually been brought up ever. It wasn't in the GPs, and I don't recall that it ever was in the Q&As or anything like that. Yeah, and unsigned, it'll go double the number because it doesn't have to deal with the negative. It's in one of the pre-course videos, Ryan's saying. Cool. And then right here, we're just going to create a stack. By pointing to the struct that we just defined. And the only thing we need to pass it is the unsigned int capacity. No, I don't want to change this. It's caused problems before. All right, so we will allocate the memory. Size of the struct that we've declared above. We're going to set the top to -1. I think that'll be real clear while we do that if you don't realize it intuitively here in a second because of the iteration that we do. And then the data is just that array that we're creating and we're going to malloc the capacity times size of int. And here we will just return the stack. Brad's asking, can you remind me why we put the name at the end? Okay, Sean's answered that. Cool. So Sean's answered that question. Here we're making an is full. This is just going to be a check to see, is the stack full? So we're just returning a Boolean. That's why it's of type int right here. We're going to return a 0 or 1. And we're just going to return, is the top of the stack equal to the stack capacity? And of course, because it's 0 indexed, we will say -1. This just returns a Boolean. We also need to say check if the stack is empty. The stack is empty when, how do we know if the stack is empty? What would we look for here? It's a one-liner. Yep, if the top is still -1. So we're just returning a Boolean here as well. And we will see why we're using these here in a minute, but we've used these in the past on data structures, so hopefully it's pretty intuitive. Then we're going to add a push. And we're just going to be pushing an integer here. So that's our second input. What would we want to check here on a push? Kai, we're using -1 on the top because when we push, we are incrementing. As you're going to see here in a second, we're going to increment. So this will just, and we increment before the push to move the index up. So we start at -1, so our first index is 0. Otherwise, we would have to check if it was at -1, and does that make sense? It's the simplest syntax and the most intuitive to use, just to start it at -1. And that way, when we increment the first time, it will point at 0, the 0 index. So before we push, what do we want to check for? If stack is full or not. Correct. If the top is less than the capacity. Yeah, either. Good answers. We need to see if, so we'll just use is full, give it the stack. If it's full, what do we need to do? Allocate more space. There we go. So we could say stack capacity, and we'll just say 2. We'll just double the size of it. Once again, we could say, put anything we wanted there. What else do we have to do now that we've changed the capacity? There's one other thing we've got to do before we move forward, or that line 32 is all for malloc, Kai? Realloc. And what are we going to realloc? Data. And we'll also have and then after we pass through that conditional, this answers your question right here, Kai, because we are incrementing. Remember the plus plus, just like in JavaScript, when it leads, it is doing this before the operation. You see why we need to start it at -1? If we didn't, you would be trying to push to an index that doesn't exist at -1. Does that make sense, Kai? So here we've just had the item. We're setting it equal to that item by incrementing the index. Line 37. Okay. So this is clear. This is just reallocating space. Remember, we've got three things here. We've got the capacity, which is a set number that we fed into it originally, right here. The top starts at -1, and this line 15 right here for data, the key data, is pointing to an array of integers based on the capacity. Same thing that we've reallocated here, okay? So now we're just saying the stack data at this, using array notation, this is just going to be 0 for the first one, because we incremented from -1 to 0. Then the next time around, it's going to be 1. The next time around, it's going to be 2. We're just assigning that value to the int that we took in. Can we do line 34, stack realloc, or do we need stack?
Yeah, I don't think line 34 looks correct. I think Addison's right. We have to do stack data equals realloc. So I don't know if that's a typo.
Yeah, I'm looking back at it right now. That was a typo on my behalf on the realloc. So that looks right. That look right to you now, Edison? Thanks for the catch. No, no crazy black magic. It was me talking and typing and looking at the feed all at the same time, and it just totally slipped in my mind in a typo. But like I said, good catch. And then if we got to push, what else? What's the last thing we need to put here? for this data structure. Yep, a pop. And if we're going to pop, what would we maybe want to check for first? Yes, we're going to see if it's empty. So we can just invoke the little helper function that we created above. Kai says, oh, so realloc requires 2 parameters, the original malloc and the size you want to give it. Yeah, and remember, Kai, that when you realloc, another cool thing is it copies over the information that you are to say you had, like we had earlier, you had 50 spaces and you reallocated it to 100 spaces. The first 50 spaces will be reallocated with the information that was already stored in them. And then we've got our new space that we're at. That's a little something that C actually does for us. So we're going to check. We're just looking for a Boolean. Remember right here, we're not using void, we're using int as the return for pop, because what happens when we pop something in general? What happens in JavaScript when we pop something? What's it return? Yeah, it returns the last element, and since it's an integer here. So if it is empty, if this reads to true, the conditional just returns a -1. And then here, what are we going to return? Yeah, James, the last value. What do we want to return here? What's the syntax? The last value, how would we get that? Remember, the data is where we're storing everything. Need to go to the top. There's one thing I'm missing here. What am I missing? Well, we're not actually, yeah, Justin, we're not actually removing it. We're moving the pointer. So remember, we just need to decrement. Why do we have it here and not here? Why does the minus minus after and not before the top, like we did the plus plus? Yeah, after the operation, because we want to return the value that we're popping, and that's the current value that stack top is pointing to. And then we decrement it so that we're at the correct spot, because we've popped that. We haven't actually removed it. It's still there in memory. But like we were showing earlier and talking about earlier, we've moved the pointer so effectively we have popped it off of the stack. But it's still accessible in some cases, like we saw earlier. But it's invalid. Right here, Addison. I mean, it would have been like me just doing this. I actually put it in the wrong place because I went behind top. But this wouldn't work because we need to decrement afterwards, but right here is what you're asking about. Right there. Cool. Yeah. It was just because we started at a -1 index. So then this moves it to the 0 index, the 1 index, the 2 index. Here, we want to go right here because we access the current index, return it, and then we decrement so that it is logistically where we want it to be. Nedim, do we need to realloc now to free up that space? Well, no, because what if we push onto it, we'll just override it. And we've already got remember, we've got a set capacity. Now when we push, it'll just, if the next operation is a push, it'll just overwrite the value that's still sitting in there in Never Never Land. Does that make sense? Any more questions? And then we're going to implement the tests and James says, I kind of see JavaScript object.address equals value is to C's object. And then that address equals value helps me remember. Okay, so we've got everything here now. We define the struct stack. We're creating a stack. We have a helper function is full and is empty. It's just based on Booleans. We have a push that uses the is full and adds the item and handles the index. After it checks and reallocates space if we need, and a pop that just simply checks if we're empty and returns a -1. And then in practice, pops the value. So Kai, on line 45, we're returning the value that we're currently pointing at. The top of the stack is what we're pointing at. We're returning that value because that's what we do in a pop. Then we're decrementing the top by 1, effectively removing the value at that index because we're now pointing at the index behind it. It's still there in memory, but it's no longer being pointed. The pointer has moved. Like we saw earlier, you can still access that sometimes, but it's invalid. And if we push it after we popped, if we push immediately after, we would just overwrite what had just been popped in the memory. We're returning the value that was popped because it's the value right here. See, stack top, we're returning this. Return stack data, the array of our data, and we're returning the top. This occurs after the operation. It's returning this. It's returning stack. Say we push to the first index, 0. This is returning what's at the 0 index using array notation, what's at the 0 index of this array that we're using in the stack to store all of our data. Yeah, and then after that's all happened, we do the minus minus afterwards to decrement. Yeah, I mean, you could do this in 2 lines, but it's just syntactical. And it makes it really easy because we need to decrement this, and then we've got our return here. So we would have to, I guess, go back through here off the top of my head, and when we initiated the pop, you would have to decrement back. But then once we've decremented, then we've got a problem at returning this. So this is just by far the simplest, most clear, concise way to do it. Do you understand? Does it make sense what I just said, Kai? It definitely does, but this would be hell for anyone who came from any other background. Yeah. When we come into here, if we decremented first, then we wouldn't be we would have to change this and increment to be able to point to the current one to make the pop return. And then the decrement would be handled the next time around, which just doesn't make sense. So in this, we're accessing in the array that index. Like I said, if we had just pushed once, it would be the same as just going into the first index, the 0 index, returning what's there like a pop does, and then afterwards, after the operation, doing the minus minus. Remember, if it's here, it does it before the operation, same as in JavaScript, same as in many languages, could be all languages. I can't think of an example that doesn't do it, but I only know 1, 2, 3, 4 languages fairly well. And Sean makes a good point. It's a terse way of doing it, and I mean, it makes sense to me because I looked over all of this before, and I've done this before 2 times over. Yeah, true. There's a way that another way that James did it. And that's perfectly valid, and it's much more readable. But I think, yeah, this is generally how I've seen it when you're out, whether it's Stack Overflow or you're seeing an implementation of it. But you definitely could do it in the more readable way. Here, the int main is just creating a stack, and we're going to make it capacity full. We're saying we're going to print stack is full. That should return false because it's not full. Stack is empty. That should return true because at this point it's empty. We push 10, the value 10, onto the stack. We test is stack empty. That should return false. We push 20 onto the stack. We check is stack full. Now that because we have a capacity of 2 and push 10 and 20, we say this should return true. Then we pop. Remember, we're popping off the top, so we should get a 20. Then we pop, we should get a 10. What are we going to get here for when we pop? -1, correct. Then we're going to make a push count of 100,000. Printing, we're pushing 100,000 things. This is just telling us what we're pushing. We're going to iterate through from 0 to 1 less than the push count and push, as we've done before, the same value to that index. So 0 to 0, 1 to 1, all the way up to 999,999. And we're going to pop everything. From the stack. We're going to start out initialize at the push count -1 because remember we have 999,999 before we're 0 indexed. We're going to run it to I is greater than or equal to 0, and we're going to decrement each time. We're going to say int v is what we're popping off the stack. Remember, we're returning the value that we're popping. And then this line kind of, it says if v not equal to I, print popped, and it'll give the value that it popped, but we expected, and it'll give the value that we expected, and it gives it v and I. I think I know the answer to this, but I'm actually not 100% sure, and it's not a trick question, why it does what it's about to do. So I'll let everyone comment on that, and maybe Sean comment on it. And if we have no mistakes here, I should be able to say GCC wall stack. Warning, I expected this warning line 17. Looks like I got lazy and nobody caught me. I forgot my semicolon. So go back down here and try this again. Comparing an int to an unsigned int, which once again, that's just all of the warnings that we're allowing. So we'll go ahead and run this stack. And remember, we had a lot of Booleans. Remember, for the first one in the test, we initiate a stack of capacity 2, check if it's full, false, check if it's empty, because it returns a -1 because we've done nothing to it, true. We push to the stack, 1 item, integer 10. We check to see if it's empty. It's a false because now it is not empty. We push again, the 20. Now we've reached capacity. We check to see if it's full. We return true. We pop from the stack. That's going to first pop the 20. We get 20 popped from stack, 10 popped from stack, -1 pop from stack because, like Brad mentioned, it is empty, so our helper function is empty, is returning -1. Then we pushed 10,000 things, and we popped 10,000 things. And if we started, what could I do to mess this up? And because I changed the increment, I started with the push count at 100,000, excuse me, and did not start it at 99,999. I guess I've been misspeaking each time. We started at 100,000, so it's really going to 99,999, not 999,000, as I just realized I've been saying. Because we start at the wrong index, we have our catch here that prints out. And you can see now that it is functioning. And this is going to go all the way up and up and up and up and up. And let me, before I drop this, since I made changes, run this one more time. It is correct. I will drop this into the channel, and we will move on to the queue. Give me 1 second here. There's the working code for the stack. I'm going to make a poll real quick here. We have a queue that we can implement in C. We'll go through it the same way that we just went through the stack. It might run over the time. I'm willing to let it run over. You don't have to stay around if you don't want to. I can just drop the code for it if nobody wants to see it. All right, everybody wants to see the queue. 6 people, yes. Nobody's saying no, so give me 1 second. And everybody, you can take about 3 minutes, so maybe about 46, 47 after the hour, just to let your brain clear real quick, and we'll implement the queue in the same way. All right, so whoever voted no, feel free to take off. I will drop the code. This is all being recorded, so you can get it later on if you like. And thank you for your time. And about 2.5 minutes here, we'll jump on the queue. I'm going to take a quick break and grab a glass of water. So I'm going to put my mic down for just a second. Okay, so we are recording. I've got the mute undone. I'm sharing my screen. We're going to implement a queue. I saw Justin said, what if you have a -1 stored in the stack? How would you differentiate between popping the value -1 versus an error because the stack is empty? Well, Tommy, the -1 that we start at is the pointer address, and then we increment it up to 0 when we push that first value. But remember, when we iterated, we also are assigning the same value. So 0 is the index 0 is the integer 0. Index 1 is the value 1. So I think Justin's asking if we pop, and let's say we index 2 was -1. The way we've got it set up is it would return -1. But remember, Justin, if you go back and look in this code, when we have is empty, okay, the way it's written, it wouldn't catch that. It's expecting to be the index equals the value, and because the index would not equal the value, this test would not be valid for that. You caught a hitch in. It's just a really simple example that obviously in the world or in any other circumstance would not work. This test was just set up to show that it was functioning or to show that there was an issue. So we'd have to rewrite the test in a different way, but it would catch on there, definitely. Good note and good catch. And we're going to go ahead and start. Yeah, and Sean's going to stick around for the queue. So I'm going to go ahead and start implementing that. Once again, ask your questions. They're all good questions. And we have our preprocessor information. Right, so we did the stack. Now we're going to do a queue. So the first thing we need to do is the same we did with the stack. And something that this relies on is the previous code. So we will account for that. Here in a bit. Because the underlying structure is just the same. It's the operation later on. Once again, we just take in an unsigned for the capacity. We're allocating the memory with malloc. It is, James. Remember, I was saying what it's. I'm going to put that in the end. I'm just going to cut and paste the stuff back in. I just made this a separate file, so we didn't do this all on top of each other, so that they're separate files. All right, with the queue, what operations are we going to be looking for? When we deal with the queue, what are the two things that we normally do with the queue? On queue, DQ. Yep. And so, Justin, to answer your question a little bit more, now that I've got my eyes away from the computer, the stack implementation, it just takes, it's just, it wasn't all redone here because we can see if the stack is full when we're pushing, just so it's just saving a little bit of time. So we're reusing code that we already had. Makes sense for now? Yeah, we're just going to be using the same helper function is full, and we've got the capacity, the top, the push, the pop, all that's already available. Remember doing this in other data structures when we did it? I just didn't want to dump the code in right away to make it more confusing. But I guess I made it more confusing by not including it. Cool. Tommy, are you agreeing I made it more confusing, or just saying you see what I'm saying? So here's our on queue. Okay. Well, I apologize about that. It's a lesson learned. So here for the on queue, we're just taking in the queue as the first argument that we've created. And the same, we're taking in what we're going to on queue. Okay. So because of the nature of a queue, remember a queue is first in, first out. It's not like a stack where it's first in, last out. It's first in, first out. So it's like a line at the bank. The person that was first in the line is the first person that's going to be served, and the line is treated accordingly. When we push onto it, we can use the same push that we did with the stack. So once again, we're just reusing code. Remember, in the push, we also are checking what's preferred, top or bottom. I don't understand what you're at. Is it in the, you mean in the code you're asking? The standard way in C is the this way. Yeah, it doesn't matter at all, but traditionally C was written like this. Yeah, it's Sean saying it's just convention. I just went back over to the stack code, and I'm going to put it all in here since. So this is the code that we just did with the stack, with the is full, the is empty, the push, the pop. It doesn't have the tests in there, and it doesn't have the preprocessors repeated in there. Yeah, Kai, like I said, I realized after we went through the first 3 reviews that this no way was going to be done. And it's lunchtime right now, so you got an hour for lunch. This will be on video. I'm going to keep implementing this. There's actually not too much more left of it. It's just the DQ, and then I'm going to paste in the tests and we'll run it. But if you want to take off, feel free to take off. So this is just right here. This is just using the push, and if it comes back less than 0 because of what we did here, then we're just going to say the queue is full. And then we move on to line 66, which just prints what we've on-queued onto the queue, which we'll see. And then for the DQ, we're going to have an int again because when we pop, we return that value. We're just initializing top and result. And now we're using the pop that we previously implemented in the stack to DQ. See, Tommy's typing. Isn't top getting the last item that was added to the queue? Oh, but I think you'll see. I think you'll see what's going on here, because then we're going to say if is empty. Remember, we initialized result up on line 71. Does this make sense now to you, Tommy? Why? Yeah, I'm letting Sean type. Yeah, yeah, Sean, this is the one. I remember earlier I said that I was a little bit confused and I thought it was the stack that gave a weird result that I didn't understand. It was actually this one. And it took me a minute to figure out why it was doing what it was doing, but you're going to put the better version. Sean's going to put the better version in the channel. But if I've got all this right, should be able to put these tests in, create a queue of size 100, on queue 10, 20, 30. And then DQ 3 times and get 10, 20, 30. What is it catching on 62 and 63?
You're missing semicolons, John.
Story of my life. And that, where's the others? It's still giving an error on 60, it's saying 62 right here. Pointing to the invalid operands to binary expression.
Oh, that's saying
It doesn't like this.
push doesn't return anything, but we're checking to see the return value of push if that's less than 0. Okay, I just realized this queue implementation has problems that I did not catch before.
Because the push is checking up in the push, it is using the is full, but we're checking is full here. So that I think down there you were trying to talk of whether you were trying to, yeah, it doesn't return anything, but I think you were thinking about this right here.
Maybe, yeah. Yeah, I need to redo this. Like completely. It has problems. In fact, I think I'm just gonna have to like rewrite it right now. So I'll post a better version in Slack. We can once I've written it, we can talk about it in the afternoon session too, if you guys want. But yeah, right now I don't think this is gonna work as is. So I need to go ahead and fix that.
No, it's not working because it's on queuing, but it's not dequeuing, right? I just went and commented out the section where we're trying to catch it.
Yeah, sorry. This was a bit of a wash.
This was the one that I said confused me with the way it was coming out, and I just kind of rolled with it because I figured it would become more obvious, or somebody would catch it, or you would catch what was going on with it. But
no, it's not a great implementation. So I'm gonna go ahead and fix that.
All right, so we'll just. Does anybody want this code so they can play around with it and try to fix it?
I mean, if they want the broken code, that's fine.
Anybody want the broken code? Put it in the channel and I'll drop it. Otherwise, Sean will drop.
I'll fix it up and drop a better one.
Yeah, this is my bad, Sean. This is the last one I went through, and I went through it this morning, and it was coming out a little weird, but I figured it would just all suss out. I didn't realize that this was the case. All right, Kai wants it, so I'll drop it in there. And I'll just note that this code is broken. You could use is full and on queue, correct, Tommy? Because we've got access to it because we've got the stack. So we could say if is full, then print the message, and remember that we're checking is full actually will reallocate memory so that it would be able to turn around and on queue it. So accordingly, well, but see, this returns out of the whole on, because it's going to reallocate the memory, but then it's still returning. And so it's not even going to be able to on-queue the item. But you could rearrange. I can see how you could rearrange this now. Okay, I'm going to go ahead and end the recording. If anybody didn't have any additional questions while Sean is working on this, I'm going to go back through and try to fix it my own way. Sean, can you jump on a Zoom?
Yeah.
Okay.